Hi there, and welcome to the Accidental Geographer. My name is Vincent Del Casino. I'm the Provost and Senior Vice President here at San Jose State and the host of this podcast. Today, we have an outstanding conversation with Dr. Minghui Diao from the Department of Meteorology and Climate Science here at San Jose State University. And we're going to be talking about things at the planetary scale, at the cloud scale, and even at the local scale as we think about the interrelationship between clouds and energy and climate change. And we're also going to talk about the future of research and the questions that come from interdisciplinary work. So come on board. This is going to be a great conversation. All right. Well, thanks for being here. I really appreciate you taking the time.
Yeah, thank you, Vin. And this is a great opportunity. I actually get to share my story, hear about your story, and connect with everyone on campus.
Yeah. So I always like to begin sort of, how you got interested in what you're interested in, but also, this interesting journey from Beijing University to Princeton to San Jose State. In and of itself, that's a fascinating kind of journey. So kind of what got you interested in the kind of questions you are? How did you end up where you were? Can you tell me a little bit about that background?
Yes, thank you. That's one of my favorite questions. And this is the type of question I constantly ask myself when I feel, when there are so many things to do. I ask myself, what brought me into this field first? What did I really want to get from it? And that actually is the motivation finally pushed me to do more new things. So when I was in my undergrad, I was more interested in chemical experiment on materials, also microbiology. So I actually wrote a paper when I was in undergrad, my fourth year, on how do you deactivate something called the Bacillus subtilis, which is a substitute for anthrax. So the bacteria that we work with are harmless. They are you can find from natural soil. There's no problem, but they're very hard to kill. And my undergrad advisor at the time, he just got back from Yale University and started his first year as assistant professor at Peking University. And I was his very first undergraduate student. There's nobody else in the lab, just me and him. And we started just trying to manufacture some iron nanoparticles and try to use that to deactivate that bacteria. And he told me that when he first tried to use silver or high electricity field, is even with that much of a power, you couldn't kill all of it, maybe just deactivate 70%. And the nanomaterial generated, they actually form these needles and poke through the bacteria. And you can see them under the microscope and see the cell of the bacteria being broken into. So that was so fascinating to me. It connects the chemistry, the physics. But then there's so much. After I've done a lot of air pollution or microbiology related work, I realized the type of research I do is very, very specific. And it's a very specific chemical reaction, very specific microbe. And I tend to like to work with just, the earth and a bigger background in general. And even better if I can connect with people and share my enthusiasm about research. So when I was applying for grad school, I just spread the application to a little wider field, not only in chemistry or atmospheric pollution, but also civil environmental engineering, etc. And that's when I did my school visit to Princeton. My PhD advisor, he was also a first-year assistant professor. So you see the trend there. They're very enthusiastic. They're very motivated. You can see the sparkling light from his eyes. Is so motivated about his work. And he said, well, if you join my group, you'll be able to work with this research aircraft flying around the world, taking samples, study clouds, water vapor, global climate change. You can get to work with models. So I thought, wow, that's kind of the life direction that I can see. I can put my 50 years of life working on it, and I won't feel bored. There's so many things to do. So his enthusiastic and the motivation talk actually just lured me in. So I went to his group instead of I have another offer from Stanford, which is on the same topic of air pollution. But I'm so glad I just followed my heart. At that time, there were a lot of people telling me, you may not find it easy to change the field because you're going to jump from chemistry or biology to all physics. in the civil environmental engineering at Princeton, we take a lot of classes of atmospheric oceanic science. So a lot of them are fundamental fluid physical dynamics, all that kind. And I find the first year was pretty hard because you really were not competing with people at the same level. Everyone else came with some kind of a level of background from the same trajectory of undergrad, but I came from pure chemistry. But after that, of a hard time of catching up, it really just gave me an opportunity to do everything. I find that's the best part of working with climate science and atmospheric science. There were so many topics you can choose from. And even now, I came to San Jose State not even knowing much about wildfire. But since the Wildfire Center was built, and Craig was, again, you see the highly motivated and leadership there. He was just the natural leader for this Wildfire Center. And I felt like I have to do something, collaborating with Craig and Adam and everyone. So it just naturally got me into the field. Now I'm working a little bit with wildfire as well, maybe with public health and with wildfire impacts on clouds. So I've always just liked to follow whatever is interesting.
Yeah. Well, that's great. And you landed at the better university in Silicon Valley. I mean, Stanford's all right, but San Jose State is where the action is, right?
Yeah. And it's just amazing that there are so many great colleagues. Yeah. And, I was working on a bigger proposal last year, and then there were people that I get to know from all sorts of departments, social sciences, urban planning, Professor Boyang. So it's amazing all the great work everyone is doing.
Right.
So it just offers me a lot of opportunities that if I couldn't apply for a proposal or do something that I want to work on. So I was just talking to Bo saying, can we actually use your drone to take samples in the clouds and measure the aerosols or take some radiative transfer measurement? Yeah, so we were talking about all these things that nobody themselves could do.
Yeah. Well, I think that is the interesting question. So I want to kind of get into some of this. And clearly you have an interest at working at planetary sort of scales, like really asking big questions. But also what I hear you saying, which is really interesting, I think is a real benefit of an institution like this, is working in interdisciplinary teams, because these big giant questions can't be resolved from one field, right? So how do you think about that, and how do you find ways, how do you see that collaboration developing for you, and what do you look for in kind of problem solving? Because obviously, like, hey, I got a slice of this, but I think there's something bigger going on here. Because a lot of your papers, not surprisingly, then have a lot of people on them from all different kinds of places, not just San Jose State, but you're working across institutions as well, right?
Yeah, so maybe that's actually part of the learning experience as well. I'll talk from my own experience when I first got here. How did I even branch out and develop more field? When I was in my undergrad or graduate student, I was mostly graduate student. I was working on this specific type of cloud called cirrus cloud. It is so unique that there are not that many researchers even work on that, even in the whole globe. You can count them. Maybe I told my student you can count the top groups in just one or two hands, and many of them are retiring. So not many people even study cirrus cloud. But lately, recently, because of the climate impact, there are a lot more emphasis on cirrus cloud. When I was a graduate student and got to San Jose State, that's all I was working on. Everything about aircraft observations or satellite observations, modeling, but all about cirrus cloud. But then around the time I got to San Jose, there was this big science question about a big climate model error over Southern Ocean. And the reason they were wrong was because they couldn't figure out what kind of clouds they are over the Southern Ocean, ice cloud or liquid cloud. Simply a thermodynamic phase difference could cause a huge difference in the climate impact. Say if we think that there were a lot of ice cloud, that will actually provide like a buffering effect. We warm the surface, but the ice will melt to liquid. So it will buffer our global warming a little bit. But in reality, what is actually a little concerning is we went out to Southern Ocean and make a lot of observation in the recent years, 3 to 5 years, and realized, wow, there were a lot of super cool liquid water there. So they're not ice cloud. Then we probably were too optimistic, putting all these ice cloud in the global climate model, thinking they could actually buffer the warming effect. So that could cause a huge difference on how we project the future. And we know every little temperature increase for a global average could have severe consequences. So when that topic came out, I was not in that at high latitude or mixed phase cloud research community at all. I don't know much about clouds containing liquid. I was working on solely ice cloud. But I was here for the first 2 years. I feel I have this academic freedom, which is really important. Nobody, come to say you gotta publish 5 papers a year to just keep yourself on the treadmill, just publish for the sake of publishing. Instead, I talk to my colleagues. They encourage me to pursue some just new ideas, some topics. There's no homework assignment, like every month you have to do this or that. So that is the freedom I think get me into, I'll spend the whole 2 years. I may have not much paper publication in that 2 years, but I'll become an expert in the mixed phase cloud field. So the first student I had and myself, we were the only two working on this. We developed this algorithm to identify cloud particles through aircraft measurement. And after we got our first paper published in Journal Climate, I was able to apply to multiple grants, National Science Foundation, Office Polar Program, and the Department of Energy. So it just started to come in because now all of a sudden I become the expert, which was not possible back in 2015. I have no idea what the mixed phase cloud is. So that kind of gave me the confidence. Well, if I can learn something from scratch and become the expert of it, I could do the next thing. Yeah. So I had my eye on this air pollution, public health impact, PM 2.5, the small fine particle. Right. There are so many things we could do about public health now because it directly affects everyone. Yeah. If you have observation from satellite data, ground observation, you have wildfire, ultimately people ask you the question is, what does it mean to me, right? Yeah, you talk about global climate change and you talk about on average, temperature is going to increase. It's hard to figure out how do I feel day by day. That's the part that people find it hard to feel the average change, but they find it easier to understand extremes. So wildfire and the air pollution incident is kind of like this. When it's really dirty outside, everybody can feel that our lawn was burning when there was a big heavy smoke. And then people start to ask questions, how can we make it better? And the reality is almost everywhere else in the United States, the air quality is getting better, except for the West Coast, and due to the recent years of wildfire. Yeah. So that also is a connection to the wildfire center. So we.
Yeah. Well, what I love, there's so many things I want to explore here that you've talked about. One of which I really enjoy is that being in a place like San Jose State actually gave you the freedom and the space to think. And I think that's often undervalued when people first go out on the job market. I got a job at Long Beach State back, my first job, and I thought, I'm going to work hard, and then off to an R1 I might go. 11 years later, I'm like, the best thing I ever did was stay there and develop my career. And I 100% just like you, I found myself doing different things with people I wouldn't have necessarily been able to explore with. And I think that's a really valuable thing because then we instill that sort of energy and creativity in our students, our undergrads and our graduates to go, again, problems take time to think through. You can't just solve them tomorrow. And what happens sometimes is you get forced to stay really small in the work because you got to get it done right now to get it out. So I guess it has facilitated your ability to kind of go bigger and bigger. But even going back early in your career, right? You're doing work on the Arctic Ocean, right? You've been doing work on atmospheric observation. So you've ended up in all these different conversations in different ways. Tell us a little bit about some of that work on methane, some of your questions you were asking earlier on in your career, and then how that informs some of the things you're doing today.
Yeah, so that's another great question. Maybe I'll talk from the perspective, how I started from all these observations. And there are these accidental discovery. Just by accident, we discover something. And then that can actually have a lot of impact on how we project the future through simulation, for example. And the methane observation you were talking about, we were flying in this field campaign called HIPPO, HIPPO. Just sounds like the animal hippo. It was actually the first flight campaign they did, a nearly pole-to-pole observation, sampling all the way from Arctic to the circle of Antarctic. And then remember, there was one flight I wasn't flying on the plane because my instrument that I take care of, it was automatic. So we have to save the seat for whoever need to do manual work on the plane. But I remember I was looking at graphics. They have these real-time satellites send back the data. You can see how all the instrument readings are. And I remember people start checking and say, is there something wrong with the massive measurement? Why there's a sudden jump? And then they started to say, okay, let's try to go back around the area again. And then just fly over again. And oh, there's another jump. And look at the water vapor. And they started to see the correlation between different variables, how water vapor is a tracer. You can see if there's a open crevice between the sea ice, and you have some more moist air coming out. But at the same time, there's more methane. So they started to wonder, is there something wrong with our instrument? How could there be this high methane reading in the middle of nowhere? This kind of linked to when people discovered the ozone hole. They didn't just discover and immediately reported it. The first reaction scientists had seeing the huge hole of ozone in the satellite data is, something got to be wrong in our algorithm. Let's fix that. It's not right. It's not realistic. But then they realized, wow, this is real measurement. So that's what happened with the methane part, that we were lucky to fly back and forth 5 deployments from pole to pole through 3 years of time. So every time they flew over what they call the leak, they would actually, they would actually see these high methane. And then they were trying to hypothesize this is probably from biological activity instead of a far away human emission, because that would not be always correlated with where the lead is. And that lead to Nature Geoscience publication. Just amazing. It was maybe a few minutes of data on the plane seeing a sudden spike, but people watching the screen all the time noticed that. Yeah.
Well, it's interesting, I mean, I called the podcast The Accidental Geographer because I fully believe my life is a series of accidents and I've been lucky enough to be in places where I get to enjoy that. And I think that's such an important part of science, right? Because, and the interesting thing is how that sometimes disconnects from education, because we're like, you have to get the answer right. Mm-hmm. But the truth is failure is a finding, right? And it's also a way to test ideas. So how do you think about knowing that serendipity, that opportunity, those accidents that you've been able to have in your career, how do they translate into when you're working with other students and so forth, and getting them to think it's okay. It doesn't have to read the right way. We might actually find something or we might find nothing, and therefore we have to change our question. We have to rethink how we're doing that. How does that play into sort of your role as a mentor of students, of other colleagues? You're now an associate professor. You got assistant professors who are going to come in. They're going to feel like I got to nail it all right now. So how do you think about that?
Yeah, thank you for that great question. I have to say that's one of the reasons I think I stay in a university, because being in a university, you're constantly also being motivated by your own students. You see how passionate they are. They come in so driven to help with the climate change issue. I have multiple students actually told me that they took my undergrad classes or they heard about cirrus cloud. I didn't even know students would hear about that. And that a few months ago, I had an undergrad student walking into my door and said, I want to do my undergrad thesis with you because I want to study cloud. And they told, everyone else told me I should talk to you. So it was great. It made my whole day just thinking about somebody is just naturally so inspired by these phenomena like cloud. And one thing I have to say, I have been very, very lucky. All my students, they are actually decided to stay in academia, and they want to make part of their contribution by working with climate change. So I have probably on the order of 10 students now graduated. Most of them are in their PhD. Some of them are already starting to get postdocs. So it's great to see that they're working on all directions, but still very motivated to keep working as a researcher. And I would say one thing I always tell my student is just never be afraid of doing something. The most important thing when I talk to them is you sit down, you think about what is the thing that you really want to do. Let's not be boggled down by just all those technical able or not able to do this or that. Not about coding, not about instrument availability, not about if we have a satellite or not. Let's just talk about what do you really want to do. And when you get that right, when you get that question in front of you, then you realize you can be unstoppable, because everything else, you just need to find the right collaborator, find the right data set, find a new satellite data set that just got, there are quite a few being launched lately. So then you can naturally lead to that path. But I try to tell my students, don't try to lower the question you try to ask just because you feel like, I may not have the right data or tool to do that. And also don't be afraid to break anything, because most of our group members, we work on computer. Worst case, the MATLAB crash. Just throw at it, try all the stuff, try at it. Sometimes it's the resistance of trying to say, should I try this new thing? It's so outrageously new and nobody do it that way. But a lot of time I realized, if you realize it seems really, really new, nobody doing it, you may just be the expert, the only expert on that. So I try to tell my student that.
So that's awesome. I have to say too, what is interesting though, but I think a little overwhelming, at least is when you work on climate, you're almost always working at a planetary scale, because at the end of the day, climate is a planetary process. There are local, obviously, there are lots of people that do local climate work. So, and I know them in the fields. I mean, there's paleo people that study local climate effects. There's lots of things. But at the end of the day, too, you're also, the interrelations are planetary. There's like almost no way to avoid some of that, right? Because the interactions of what's happening halfway around the world can have that impact. Ocean acidification changes the nature of flow, which changes the nature of the relationship between land and water and air. So that's big. Like, given that, how do you think like that? How do you think about those planetary questions while also knowing I got to parse this out a bit? I got to get it. I got to get into that cloud and see what's going on. Knowing in the back of your head, though, that all this other stuff is happening at the same time. How do you balance that sort of intellectually?
Wow, that's actually great. I think that's where, when I set the direction of my group, like how would you vision my group become an expert in what direction? Am I going to copy exactly what my advisors have done? Definitely not. I feel like I set my group in a very unique location. It's between the observation community and the simulation community, between the small scale where you care about exactly what's the composition of this little particle to the part that this will influence the next hundreds of years of prediction. So I think that's the unique part of my group. I may not only study in the lab, capture particle by particle what they are made of. And I may not try to develop my own model, but I get the connection with the field collaborators in both fields. And the way I'm looking at it is I may be like a problem solver. So one thing this year I find really fascinating is about this climate geoengineering topics. So I just got back from this conference called Atmospheric Meteorological Society, and there was a high-level workshop, kind of what do you call it, like a presidential forum or something like that. They invited all the top experts and talking about where are we at for geoengineering. And I think the consensus is, even though we have known so little about all the physical processes, right now we're at a point that the action of not taking action is having so much adverse consequence, than to give it a try, to do small-scale testing. And from what I heard, there are already field campaigns going out there trying to see the low-level cloud, those stratocumulus or cumulus cloud, try to cover up the ocean to slow down the warming of the ocean to protect the coral reefs. I actually didn't know people already started testing that. And then naturally, there are the cirrus cloud. It is located at the highest altitude of all clouds, and that is the most sensitive altitude to a little bit perturbation of how much cloud particle you have or how much water vapor you have. So just last week, there was a Science magazine article came out, and it's very related to what I'm doing. They're talking about a potential geoengineering method if you squeeze out the water vapor in the stratosphere. So the stratosphere water vapor already has so little in there, but a tiny little 10% fluctuation could change the temperature perturbation on the surface by increase it 30% faster or decrease it 30% faster. So temperature have a huge response to stratospheric water vapor.
Right.
And what determines the stratospheric water vapor is the process that you inject through deep convection, huge convection from Western Pacific, and those we call the cumulonimbus cloud, the highest tower cloud around Indonesia. And that's when you pump out all the water vapor in there. So they're trying to say, can we modify the formation of cirrus cloud or these convective cloud, whatever, to get them into ice crystal and then sediment out, and then you will have little water vapor going to the stratosphere. So that idea, that paper was very, very straightforward, and they gave a conceptual idea about how much you would need probably to do this. So I think that's actually one direction people start to talk about this instead of just purely being afraid of the topic. As in from a physical science background, we need to know what are the possibility.
Well, it's so funny when you started talking about, I wrote a note, ice clouds and not ice clouds, and I was like, is that a geoengineering problem? And then you answered my question for me by saying that could be a geoengineering problem. So is that what, I know you've written recently on some synoptic scale dynamics. Is that what also got you interested in some of these broader things? Maybe not the geoengineering question, but what these larger scalar systems are. What are we talking about exactly when we think about synoptic scale dynamics, and what are you looking at when you're examining these sorts of questions?
Yeah, so these synoptic dynamic scale, they could happen in examples of hurricane or atmospheric river. The sense that usually that could have impact half of the United States. On that kind of scale, we call it synoptic scale. And the specific example I was studying was in the high latitude, actually where nobody lives there over the vast Southern Ocean. Very little people can make observations there. And the available observations are usually from years ago, buoy, so they are just surface temperature measurement, and once in a while you have shape measurement. And lately, there were quite a few dedicated field campaigns lasting over a year. They're all over the Southern Ocean area. Sometimes they are on the ship, sometimes they are on the island. So they can track these extratropical cyclones that move across the place. And as the cyclone move across, part of it will have different type of cloud. So what we're talking about is the 10 years ago, the older climate model, they all have a very obvious error that on certain part of the extratropical cyclone, which is on the synoptic dynamic scale, they would not be able to see liquid cloud. So that go back to, even though this is talking about maybe 2,000 kilometer in radius or diameter scale, these huge swiping extratropical cyclone, but then they actually influence down to a few micrometer of if you're forming ice or liquid. So everything seems to be intertwined, and it's so important to represent all of this correctly or understand them correctly. But how can we do that? That's sometimes I feel like we're just so little kids trying to, poking at a little part of
Right.
the entire atmosphere.
Right.
And not to even mention it's linked to the ocean and the biosphere and everything.
Well, that is the thing, is like, despite decades, maybe even a century of work, we're barely scratched into this larger problem. So when you think about, for you, like, what are some of the next big questions in front of you? What are you thinking about right now? What might motivate the next 2, 3, maybe even 4 or 5 years of your research career? Knowing, I suspect, someone comes with a really cool problem and you can go this way in a second and jump on board and get into it, which is awesome. But for you, what do you think are the really big questions you're trying to tackle right now?
Yeah, I think part of it will be this climate modification or geoengineering topic. And cirrus cloud, like I said, 15 years ago when I first started grad school, it was purely just physical science, some radiative effect, not so much about, wow, one day it will become one of the solution to cool down Earth in a short amount of time that we can actually afford instead of waiting 200 years. There are other solutions that may take longer. But meanwhile, with the limited amount of time, what can we do to not cross the tipping point of having temperature over 2 degrees? So cirrus cloud is definitely a key for this geoengineering topic. If you look at the two types of geoengineering, one is about the liquid cloud, but almost everything else, stratospheric aerosol, people talk about injecting aerosol into the stratosphere, kind of like the volcano effect. You have aerosol lingering around the stratosphere for a while to cool the Earth. But that has to go through a process with cloud. Anything you put in the high upper troposphere, lower stratosphere, you have to figure out what's the consequence of cloud. Because if not, you may actually got canceling out or even worsening effect if the cloud form and warm the Earth more. And cirrus tend to be actually a net warming effect on Earth. The only cloud that has a net warming effect. Everything else is cooling. So it's at such a sensitive, high altitude, but it holds such a strong key for all the other possible solutions. So we're trying to propose for a field campaign. So hold my word, maybe in 2, 3, 4, 5 years, I'll see how this is gonna go. But we are gonna try to get a research aircraft out there and try to understand how cirrus cloud forms in especially high latitudinal region.
Well, that's awesome. That's really great. Have you ever seen Snowpiercer, which is a movie about like the freezing of the Earth after they geoengineer it? And all right, well, now you have something to look at, and you'd go to what's the bad thing that could come of this? But no, it's wonderful. Thank you so much. This is an absolutely engaging conversation. I could talk to you for another 2 hours about this, but I really appreciate it. It's fantastic. Thank you for being part of our community and being such a thoughtful interdisciplinary leader here, and it's exciting to see what's going to come next, so I really appreciate it.
Wow, thank you. I also couldn't appreciate more for all the great questions you asked, Vin, and I feel like this is also like a journey to walk past myself, what happened in the last 20 years of my life, and think about what's going to happen in the future. I always find that if I only have, everyone has only one life to live. What is the thing that I really want to do? And it come back to, I still want to do science. I still want to be a researcher, and I want to make discovery every day and work with my students. So
well, we're lucky you're doing that here with us, so that's fantastic. Thank you so much.